as you can see on the chart here, so the range of the thermal conductivity actually is listed in room temperature. But if across the room temperature, there will be in a range, even though it is metal. Okay, if you see the right-hand side figure, even it's a metal, the straight line slightly decline if you increase the temperature. And this phenomena is even more obviously in a liquid. So for example, helium, air, or the water even is not a straight line. It's not a very linear behavior. It's kind of a curve. So so that's how I mentioned in the chapter 2 and chapter 3, chapter 4, we're discussing different kind of K value under different position and different temperature range. 这 K 的值不是一个定值，通常啦，你要把它设定成一个定值，是真的是一个非常simple、非常简化的，就是只有在第一章才会出现，所以大家把握一下，期中考前应该就是 K value 值等于一个值，所以不会有 PDE 出现的一个章节这样。Okay, so the easiest way we just consider as a constant. Okay, of course. Okay, so that's the exercise from the textbook, so we won't go through it because we already mentioned several similar ones. So later on the textbook just talking about if there's a gas or liquid, there's a different way of a conduction mechanism quite obvious. If you want to take a look or take a picture, if you didn't buy the textbook, then you can take a picture of it. Otherwise, I already put on into the PDF file into Google. Okay. Okay, and there's a value we're going to introduce, like I just mentioned, is dimensionless. This is not dimensionless. This is just a diffusivity. 它不是无因次值。This is defined as 热扩散的能力。How the heat going to propagate? That's heat propagate or heat transfer divided by the heat going to storage. 然后在 PDF 上这个值应该我打错是 P， 我把它改一下，这个是 low 这是 density times the specific heat. When the density not divide times the specific heat means the heat capacity 热容 okay the heat capacity per unit of volume. Then if we divide the K by the heat capacity, we call alpha. This alpha is thermal diffusivity. 热扩散的效率。我们等一下写黑板的时候会再讲更清楚一点，但是这边先记得这个thermal diffusivity 是两个material 对于热处理的比值。Okay, so K divided by low and the capacity, the specific heat means the heat, how much heat is going to conduct divided by the heat going to store inside of the system. 就是它除热除能的能力对上它把热丢出去的能力，这个东西叫做扩散效率。这个会跟我们后面在讨论真正的 Fourier law 的heat equation 会有相关。之后我们还会再讲到，现在先认识一下，因为课本当中在第一章就破梗的爆雷讲了，所以我们就现在这边讲。换照来讲，是后面推导的时候我们才会提到。OK。什么地步？哦，对啊，对啊，怎么了？
这个大家去聊。
哦，怎么问我呢？我也不知道。他可能因为后面有一些题目要叫你算 Crispy 的那个里面内在会变温度几度，所以他把肉也放进来这样。OK。所以之后需要查表的话，可以看一下这边。OK， 在这边的 thermal diffusivity 这个地方呢，就是只要记得 the larger of the alpha, the faster the propagation of the heat into the medium。你只要 alpha 越大，就表示你传导的能力大过于储能。OK。Okay. So before we move to the convection, there's one thing we're going to address. So this is the most insulated solid material in the world we know. So the textbook specifically highlight this kind of material called aerogel 气凝胶。然后这个是一个 super insulating 的 material， 尤其在它的机械性质，然后以及它在航太上面的应用非常非常的重要，所以在 textbook 上面它特别来highlight 的这件事，所以我们也来看一下这个video， 稍微了解一下它的内容，我们是接触一下 high tech。I don't know if there's a sound. There's no sound.
1.22 grams.
Oh, it's very light.
That's only a few times the mass of the same volume of air, which kind of makes sense because it is 99.8% air.
And since we have
aerogels are so light that if you remove them,
a little bit.
they would be less dense than air. I have long been fascinated by aerogels, so I actually flew out to aerogel technology in Boston to find out why was aerogel invented? How is it made? Why is it such a good thermal insulator? And what is it used for?
Okay, we are going to try an experiment to demonstrate the insulating power of aerogel. So over here we have two setups, one with a glass petri dish and the other one with aerogel on top.
Both are made of silica, but with very different physical structures. We're going to see how long it takes to melt these chocolate bunnies with a Bunsen burner.
Have a look at this experiment. We have a FLIR P1020, which can see temperatures up to 2,000 degrees Celsius. Yeah, you can see that. The glass is getting really hot already.
And after just a minute,
It's starting to smoke. It's definitely melting and smoking. Oh yeah, here we go. Let's say there's a phase change.
We've got liquid chocolate situation. We have some smoky bunny. Over here, the bunny is actually sort of melting over, and look, it's sort of tilting to the side.
Alright. I think we're gonna call that an house.
What is that?
On cue.
not only did the bunny melt quickly, the petri dish cracked under the thermal expansion. So now let's try the aerogel. So how was aerogel invented?
Back in 1931, a guy named Professor Samuel Kistler had a bet with his colleague Charles Learned.
Now the bet revolved around jellies, like peanut butter and jelly jellies. And the thing about jellies is they are actually a combination of liquids and solids. I mean, they're mostly liquid, but it's embedded within this 3D solid structure.
So if you think of jello, jello has a skeleton with nano-sized pores that gives it its rigidity, and then that's about 1% of the jello.
So the bet was this: could you remove the liquid from the jelly without affecting the solid structure? I mean, if you just evaporate the liquid out, well, then the solid structure shrinks. Because as you remove liquid molecules, they pull on each other, and they pull on the solid structure around them, basically crumpling it from the inside. Now, Samuel Kistler solved this problem in two ways. First, he realized you could replace one liquid with another inside the jelly just by washing it thoroughly. So you could swap out, say, water for alcohol. And then, if you take the jelly and put it in a high-pressure vessel called an autoclave,
By heating it to the high temperature point called the critical point of the liquid, that liquid transformed into a semi-liquid semi-gas called supercritical fluid.
at this point, there is no longer a distinction between liquid and gas. Those molecules are no longer pulling on each other.
So once you depressurize the vessel, that solid skeleton, that 1% of the mass of the gel, is left behind intact, except for where there was liquid in the pores before is now gas. And that solid skeleton, that nanopore solid, is what we call aerogel.
Kistler published his findings in Nature in 1931.
It is getting pretty hot, as you can see through the thermal camera.
But coming up on 3 minutes, there's still no sign of the melted chocolate.
So we're gonna pull out a thermocouple and just check the temperature underneath the bunny, like underneath the aerogel, and see what the flame temperature is. You can kind of see that the parts of the bunny are getting hot, but it's not the bottom of the bunny, it's all the around the bunny.
Exactly. That convective heat is moving up and around the aerogel.
So you can see the thing is getting red hot.
And by 4 minutes, the bunny is looking a little soft.
Pretty good, considering how easy it is to melt chocolate.
Can I put my finger here? Be careful.
It's not that it's hot, it's that it's grilled.
Right.
But yeah, totally cool to touch, right?
It is just warm to the touch.
He made aerogels out of all sorts of things. He made them out of eggs. He made them out of rubber, out of nitrocellulose, and included there is silica. Actually, right here on the table, I have some examples of some silica gels. This is a wet silica gel. It's kind of rubbery, so I can just, carve out a piece. It is 97% alcohol inside its pores, and then the remaining 3% solid is amorphous silica. Just, absolutely. It's kind of rubbery, not that strong.
So was I cracking it there, or was it
No, whoa, very easy to write, very probably.
The next step is to replace the alcohol in the gel with liquid carbon dioxide.
We're about to see liquid CO2.
The liquid CO2 has the advantage of being non-flammable, plus it's got a low critical temperature.
Open up, and it's floating in. Yeah, it's floating in, there it goes. It's another salt.
You can clearly see that there's so much cooler on top.
I knew I was underwater. I just didn't realize I was this underwater.
What temperature is it on bottom?
We're at 600 right now. 600 Celsius. That's 1250 Fahrenheit right now.
What's weird, the bunny is melting. It's melting right on that edge where it keeps like flames kind of crawling up and over. So yeah, that's
Oh, bunny down.
well, not a bad result.
It's not a bad result at all. I'm interested in tasting some of this chocolate here. It's warm and delicious. That was great.
Once the liquid CO2 has filled all the pores of the gel, it's time to take it supercritical.
It was, I would say, kind of a spiritual experience the first time that I saw supercritical fluid.
I love how much you're into these other things.
I love it. Make a supercritical fluid. We can heat this with a hairdryer, actually.
As we approach the critical point, the surface of the liquid becomes kind of blurry.
That is like weird waves.
Yeah, I'll speed it up so you can watch the surface disappear altogether. You're now looking at the supercritical fluid of CO2. In this state, the CO2 can be vented without affecting the solid structure, and what you're left with is aerogel.
If you look at aerogel on a light background, it's almost impossible to see because it is pretty transparent. But if you look at it on a dark background, then you can see that it has a slight bluish color. And it's bluish for the same reason that the sky is blue. Because all those tiny little nanoscale structures, they scatter light according to radio scale. And the intensity of light scattered is proportional to 1 over wavelength to the power of 4, which means it scatters shorter wavelengths like blue much more than it scatters yellow or red.
And for that reason, aerogel looks opaque in the ultraviolet and transparent in the infrared.
Now, what do you think this would look like if I held it up to the blue sky? What do you think we would see? Would it look ultra blue? No, it looks yellow. And that's because the aerogel is actually scattering out that blue light. And so what passes through and makes it to our eyes is the longer wavelengths like the yellows and oranges. It's basically the same effect as looking at a sunset. When you see the yellows and oranges of a sunset, it's because the blue light has already been scattered out by the atmosphere. The light had to pass through before it reached your eyes. So effectively looking at aerogel against blue sky is like looking at a purple sunset.
The nanoscale pores of the aerogel are also what makes it such a good thermal insulator.
You might think that because aerogel is largely comprised of air, like 99% air, that it has the same thermal properties as air, but that is not correct. It's actually a better insulator than air is.
That's because the width of the pores is smaller than the distance air molecules travel on average before colliding with something, their so-called mean free path. And it's really difficult for the hot, fast-moving air molecules below the aerogel to diffuse through it and transfer heat to the top of the aerogel. This is called the Knudsen effect.
It is so weird because, you know, you don't expect something that's transparent to block the heat that well, but this really does.
这个自由移动半径非常重要。现在 aerogel 的 study 想要一直突破的话，就是去控制这个气体振动的半径在那个固体当中的距离，那你可以有效地在生产出不同的气体胶。
NASA has also put aerogel to more exotic uses, notably to catch dust from a comet as part of the Stardust mission.
So the particles were traveling about 6 kilometers per second relative to the aerogel. So when they hit the aerogel, because the aerogel is a very low density material, very, very porous material, the particles actually enter the aerogel. And as they travel through the aerogel, they basically create part of the network that makes up the aerogel, and they lose energy in the process and eventually come to a stop. This is good for capturing particles because if a particle like that would hit a solid surface, then it just stops, immediately
And just vaporizes.
and vaporizes.
So should we expect to see aerogel in our everyday lives anytime soon?
One of my running jokes is when they build skyscrapers in Antarctica, they'll use aerogel as thermal insulation.
Why do you say that?
Well, because they don't really care about how thermal efficient it is, because it can be so cold there.
Right.
So instead of having, 10 feet of fiberglass insulation, you can have 6 inches or something of aerogel.
The scientists are currently working on reducing costs and increasing durability.
That's true. They do have some less.
Okay.
There we go. So it's not hard to break.
They've already made a lot of progress. For example, original silica aerogel is hydrophilic.
There we go. Now this is a hydrophilic aerogel.
So once we've done this, is that piece of aerogel ruined now?
Pretty much.
But there are ways to make it waterproof. So if you want to see that and all the other next generation aerogels, then subscribe to the channel, and this may be the start of an aerogel trilogy.
Okay, so that's a brief introduction of the aerogel. So if you are interested in aerogel, actually in our university, quite a lot of professors are working on the aerogel. So you can check the most of it in material engineering department. And but it's still quite a good material which can help you to put it into your I don't know, in the project if you would like to do. As you can see, the manufacture of the aerogel isn't that complex. So it has a liquid CO2, then some of the high pressure vessel, then you are able to make it done really complex system. Yeah, so just give you some idea about this kind of a super insulating material. But we are going to move to the convection. So in the chapter 1, we will briefly describe 3 phenomena, and then we move to more detail of the convection. So we talk about a little bit about the heat convection. Okay, so the heat convection has a concept of the medium, which the heat going to transfer is going to move, or there's a liquid around the system. So if we have a moving liquid, so either air or water or liquid, with temperature difference with solid surface, for example, then the phenomenon between this temperature propagation we call convection. So for example, if you have 2 plates, and this one have a higher temperature, hot, and this is cold, then you have a liquid inside, either air or water, then you have this kind of motion. Quite obvious, right? Or if you only have a surface like this, and with temperature T warm, then temperature fluid here with the direction of Y, then you have this kind of temperature propagation here. Discussing about the heat going to transfer from the solid to the liquid. Okay. Similar to the conduction, we also spot this kind of convection behavior in the experiments, in the real life. So by the observation, we can see the Q is also proportional to the temperature difference. It's similar to the conduction. But here we call Newton cooling law. This is for convection. Okay, so similar to the conduction, there must be a coefficient here because it's proportional, right? So Newton defined this convection, this coefficient called H. This is 热对流系数 convection coefficient. And will put a bar on it because usually it's an average number because it's also temperature dependent, like you take, and even more obviously compared with take， 这个 H 值会非常容易受外界温度的影响，它的变化非常大。那这个值 there's no such clear table or measurement to do that. So every time you want to measure the H under different circumstances, you need to run the experiment. OK， 它受形状、流体的方式、liquid property 的影响很多，所以它的function影响它的function很多，所以这个 H 值很难有一个直接的定值。所以你的实验如果要去 determine 这个 H value 的话，通常就是你要先界定你的实验长什么样子了，然后再去量 H。你如果量这个 H 的环境跟你之后要应用的不一样的话，这个 H 值就不能用。Okay, so usually we will put the average bar on it just to simplify the scenario. Okay, so if we're talking about the big Q, then that would be the same. Don't forget the area. So if you guys have a textbook or a PDF file, just swipe it into the appendix to the table. Maybe later we switch to the laptop. I can show you. Table A-9, then you can see how the temperature exactly affects the number of the H value. So it's extremely different. Okay, so the conduction and the convection. The history of the science about conduction and convection is quite similar. We start from observation. The Q is going to different, will have a relationship between the temperature difference, and then we give a coefficient in between, and to describe how good is the convection going to go. Okay, so next we're going to determine the unit of the H. Okay, so since the Q equals to H times the temperature difference, so the H will become, right? Then again. Slightly different from K, but the concept is the same. They share the same concept. Okay, and we just mentioned the H value is quite sensitive with the environment. So what kind of factor will exactly affect the H? So the H actually is the function of Fourier type 不同种的液体 flow behavior and geometry. Forgive me, have a dyslexia, so I cannot spell. Okay. 流体的种类。流动的类型。Okay, so if we talk about the flow behavior, if you recall from the fluid dynamics, we have laminar, and the turbulence. So, which one have a higher edge? By guessing. Turbulence? I think it's turbulence. Anyone objecting? Okay, no. Oh yeah, so this is the correct answer. So because of the turbulence has more unsteady factor inside the system, more vibration, so of course they will increase the conduction. So in the turbulence flow, the H value is higher. Okay. Then this is flow type. And also we have one thing called free convection and forced convection. I believe you already know this. So the free convection means is the thermal expansion and contraction due to the temperature difference. 温度所造成的热胀冷缩 this we call free convection. And the forced convection means there's an external fluid moving. If I draw it, the free convection is, for example, there's something like a temperature, like 80 degrees C, and there's no outside medium moving around, but itself causing the thermal expansion and the contraction. So the air is going to expand, so the density will change, so the flow starts to circulate. So this is called free convection. So this is based on the density difference, and it's caused by the temperature difference and thermal expansion and contraction, then density difference, then there's a movement. Okay? And the force. Like similar stuff here. Then you have a fan. Try to cool it down this hot object. Then the velocity of the